So let us see 2.4 standard electrode potentials. Standard electrode or redox potential, E theta. So these are the value that you can find it from data booklet. Okay, you can find this value from data booklet. So this is the electrode potential of a half cell measured under standard condition using a standard hydrogen electrode as the other half cell. So they are trying to tell you how they get the reading from the data booklet. So for example, let's say, I give two examples. Let's say from the data booklet, we know that Cu2 plus 2 electrons becomes Cu. Then they give positive 0.34 volt, the E theta. So another example, zinc 2 plus 2 electrons becomes zinc minus 0.76 volt. So what we need to know here is we want to know, or the first point there, try to explain to you how they get the E theta. So you have to, let's say for copper, so if you want to find this positive 0.34, so the copper have to be half of the cell. So have to be half of the cell. It's something like this. I draw out here. So let's say, case 1 here. How to find E theta of Cu. Okay, how to find E theta of Cu. So according to the statement, you have to set up half cell which involve copper. So you can do it in this way. You can put a container, a beaker. So put copper electrodes, and after that followed by the copper sulfate electrolytes. So something like this. Cu2 plus. You must follow standard concentration, 1 mole per dm cube. Okay, so you have to set up half cell like this. And the other thing that you need to know is when you want to set up half cell, when you want to set up the cell, they said the other half cell is standard hydrogen electrode. So how is that set up standard hydrogen electrode? We do it in this way, so you can see it here. So standard hydrogen electrode as the other half cell. So you know hydrogen is a gas. So for gas, right, how are we going to do the connection? It's slightly different from the copper over here. You see copper electrode is just, we put the copper solid as electrode and the copper 2 plus as the aqueous. Okay, and how about hydrogens? Hydrogen is a gas. So we have to use apparatus like this. Okay, apparatus like this. So where here you can channel in the hydrogen gas, H2 gas, 1 atmosphere. Hydrogen gas. So you can also put in the electrode. The electrode we use platinum. Platinum electrode. Okay, so this is the other half cell. And from this 2.4 onwards, we are starting our discussion about Voltaic cell. No more electrolytic already. Okay, so before 2.3 is electrolytic. So 2.4 onward is Voltaic cell or electrochemical cell, where we don't use battery here anymore. We use voltmeter. Okay, so that means it's something similar to this. We connect the two half cell by using voltmeter. Voltmeter. So this is the standard hydrogen electrode. The right hand side is the standard hydrogen electrode. So I have to mention about the electrolyte here also. The electrolyte will be the H plus aqueous with 1 mole per dm cube. So for example, you can use HCl, hydrochloric acid with 1 mole per dm cube. Then it will create this amount of H plus at this concentration. Okay, so this is how we connect it. And don't forget, we have to use salt bridge also. Salt bridge. So salt bridge to connect both sides. So what is the function of salt bridge? We will discuss later. So I just tell you how we do the measurement first. Okay, so this is the salt bridge. We label it salt bridge. Okay, so now let's continue our discussion. After we set up like this, then the voltmeter will show reading. The voltmeter will show reading. We show 0.34 volt. We show 0.34 volt. So remember your voltmeter is something like this. It's something like this. So let's see the basic structures of the voltmeter. So let's say here is 0, and then there are lots of scale there. Okay, so and then there are 2 terminals. So one terminal is in red color, another terminal is in black color. So if you still remember your voltmeter, so this is the voltmeter. Okay, so the red color terminal represent positive, the black one represent negative. Okay, so if this is the voltmeter, right, that we are using the conventional, the basic voltmeter, so we connect it here. How we know it is positive 0.34 or negative 0.76? So how we know it's positive or negative? So actually there is a way to know. Okay, so to know about that, first of all, we need to decide. Okay, we need to decide more things. We need to decide more things. First, your terminal here, okay, your terminal here have to connect accordingly, you know. So let's say, for example, if I connect, let's say initially I don't know, initially I don't know how to connect. I just simply connect. Okay, I put hydrogen, standard hydrogen electrode here. I put copper half cell here. So now I connect. How I connect? I simply connect. Let's say the red one I put here. Okay, so the red one I put red color. So let's say the red terminal I connect to the left. The black one I connect to the right. So are they going to have reading or not? So you just check the voltmeter. If there is no reading, you just turn around, just turn around. You do black one here and red one here until the reading shown. Okay, so that is how we connect the voltmeter. Okay, you have to try it out. If no reading, then you just swap and connect in the other way around. Okay, so now let's see. Let's say the connection is like this. Okay, let's say the connection is like this, and it show reading 0.34 volt. 0.34 volt. So we have to see what happens in the Voltaic cell here. So we want to see what happened in the Voltaic cell. Okay, so you put copper 2 plus here and copper here. Okay, it is 0.34. 0.34. And here you put H plus and H2. We know that H plus, okay, let's say, okay, red color. We know that H plus 2 electron become H2. The E theta is 0.00 volt. Okay, this is the value. 2H plus, 2 electron become H2. The value is 0.00 volt. This is the value. Okay, no value lah, you know. So this contribute no voltage, and this one is 0.34. So what happened is we follow the same idea. Whoever that is more positive will go forward. Whoever that is more negative will go backward. Okay, so we follow this concept. 0.34 and 0.00 volt. So we know that this is more positive. So it will go forward. For copper, for copper, it goes forward. For copper, it goes forward. For the standard hydrogen cell, this is not so positive, you know, compared to this. This is 0, you know, so this is more negative, so it goes backwards. It goes backwards. Okay, so if this goes forward and this goes backward, so what happens is Cu2 plus get electrons and change to Cu. Change to Cu, so they get electrons. So copper get electrons. The electron will come here. Okay, hydrogens have to go backwards. Go backwards, donate electrons and become H plus. Okay, go backwards. So go backwards and become H plus. Okay, so now you already understand how we connect the thing, and now we talk about the anode and the cathode. So donating electrons is oxidation. So oxidation always happens to anode. Always happens to anode. So because of that, this is anode. This is anode. And here, receiving electron. Receiving electron is reduction. Reduction always happens to cathode. So because of that, this is cathode. Cathode. So the other thing is you need to know about the difference between our electrolytic cell or voltaic cell with electrolytic cell. Okay, electrolytic cell we learned before, right? So that time we say anode is positive, cathode is negative. So this time it is the other way around. Anode is negative, the other way around. Cathode is positive terminal. Okay, so anode is a negative terminal, but you have to know that anode always go through oxidation. Right? Okay, although the plus and minus is the other way around already, but oxidation still happens at anode, and reduction still happen at cathode. Same as electrolytic cell. Same. The only difference is they have opposite sign now. This is minus now. This is plus now. Before that, electrolytic cell, anode is plus, cathode is minus. It's minus. So it's the other way around already. Okay. So now let's come back to the voltmeter. Is the voltmeter connect correctly or not? Actually, it's correct. So anode is negative. So we connect the negative terminal, the black one. Okay, the black one you connect to the negative terminal, and the red one you connect to the positive terminal. So the connection is correct here. Okay, so let's come back to this value, positive 0.34 volt. So how we know whether this is correct or wrong? So this is actually correct. Okay, it's actually correct. So when you have positive connected to the copper, then copper have to take positive 0.34 volt. Positive 0.34 volt. What I mean is you don't care about the standard hydrogen electrode here. So if the positive connect to the copper and it shows reading 0.34 volt is shown on the voltmeter, then this one is positive 0.34 volt because this connect to positive. Okay, so which means if you are using zinc, something like this will happen. Okay, let's say I just draw out as your illustration. I just do a quick one. Okay, so if you are using zinc, right? So here is zinc. Here is zinc 2 plus, 1 mole per dm cube. Then you connect voltmeter. Here I don't draw lah. Here I just do SHE lah, standard hydrogen electrode. So what kind of drawing is that? Is same with the top one. Same with the top one. So then you do salt bridge over there also. Okay, you do salt bridge to the other side. Do salt bridge to the other side, to the SHE. Okay, to the SHE. So let's say I just put like, okay, so never mind. I just remain it like this. Yeah, so cannot drop. Okay, just leave it like this. Okay, now how is the connection of the voltmeter? It has to be the other way around. It has to be the other way around. So which means the negative has to be here, the positive has to be there. If you don't do in this way, the voltmeter will show no reading. So you have to do it in that way, and after that, the voltmeter will show reading, will show 0.76 volt. Okay, we show 0.76 volt as in what we found from the data booklet. But how they decide it is negative? It is negative because the voltmeter use the negative terminal connect to the zinc. So you have to put the negative together. They put negative. So it is determined by the voltmeter. We use this way to decide. Okay, we use this way to decide. So that is how they get the E theta. That is how they get the E theta from the setting out of the apparatus in this way, together with the voltmeter, which have to connect by trying. Okay, so when they show reading, then you can decide whether they are plus or minus. Okay, so so far we do until here first. We have done until here, the first point only. So the next point. Okay, so after understanding standard electrode redox potential, that is E theta. So remember E theta, you can find it from the data booklet. So now we just continue with the next point. So the next point that we are going to go through is standard cell potential, E theta cell. There is a difference between E theta cell and E theta here. So E theta is where you have, let's say for example, you have half of the cell as, let's say in this case, in this diagram here, half of the cell is the copper and copper 2 plus. The other half cell is the standard hydrogen electrode. So we must use standard hydrogen electrode as one of the half cell. Compared to E theta cell here, E theta cell, this is the example. E theta cell is where we don't use standard hydrogen electrode. Okay, we don't use standard hydrogen electrode at one of the half cell. So we use any other half cell. Okay, so now you also need to know that when you use other half cell, right? So what happened is the reading that you get from the voltmeter is known as standard cell potential, E theta cell. Okay, it's E theta cell. So you need to know this is a electrochemical cell, or it is an voltaic cell. Okay, it is an voltaic cell. So that means compared to what we learned before, electrolytic cell, you can see battery here, but now it is voltmeter here. Okay, so E theta cell that we try to find out is where we do the connection as in a voltaic cell. So let's see the meaning of E theta cell here, standard cell potential. So it is the difference in standard electrode potential. Standard electrode potential means the one from the data booklet, between two half cells. So you need to find the difference. So you need to find the difference between the zinc half cell, for example, with the copper half cell. So we want to find the difference between these two, and then from there we will know the E theta cell. So when you want to find the difference, right? So we have to know which minus which. Okay, so different means we minus, right? So which minus which we have to care about also. So that is the formula over there actually. So you can see here, E theta cell is actually E theta for the reductions minus the E theta for the oxidation. Okay, so to know which one is reduced and which one is oxidized, so let's say for example, I use this to explain to you. Okay, I use zinc and copper half cell to explain which one is reduction and which one is oxidation. So you can see here, this is from the data booklet. The E theta is positive 0.36. For zinc, the E theta is minus 0.76. So in order to find out who is going through oxidation and who is going through reduction, the way is you compare who is more positive. The one that is more positive, right, tend to go forward. So that means copper 2 plus tend to receive electrons to become copper. Okay, so as you can see here, copper 2 plus receive electrons become copper. This is a reduction reaction as they receive electrons. So reduction. So the one that is more positive, the E theta that is more positive, go through reduction. And if you look at this, right, this is negative. This is more negative compared to this one. So for zinc, if they are more negative, they tend to go backwards. So going backwards, it means zinc will become zinc 2 plus 2 electrons. So as you can see here, they swap the equation already. So we have to swap. The data booklet will give you reduction form. So we have to swap, change it to oxidation form. Okay, so that is what we need to do. So as you can see here, zinc become zinc 2 plus 2 electron. Okay, and this is an oxidation reaction. So because they donate electron, donating electron is oxidation reaction. Okay, so now what to do next is, when you know it is oxidation, right? So you see the flow of electron first, because this one zinc 2 plus give zinc change to zinc 2 plus and 2 electron. So the 2 electron that produce, right, will flow this way. Okay, will flow from zinc to copper. So they will flow this way, and then copper 2 plus will receive electrons and change to copper. So electron keep going to the right. Okay, keep going to the right, and received by Cu2 plus to form Cu. At the same time, let's think about this. You have to know that Cu2 plus is a blue color solution. So the blue color solution keep changing to copper atom. The copper atom will stick to the electrode. To form brown solid, brown metal, brown metal, or we just call it brown solid. So the electrode is getting thicker over here, and the blue color copper 2 sulfate is fading. That means from blue become, the blue color gets lighter and lighter. So the color is fading. So that is the observation. But of course here, for the anode side, we don't expect any changes in color, because zinc is colorless. You can only see the anode, right? It's getting thinner and thinner. So anode is getting thinner and thinner. Okay, so anode is getting thinner, whereas cathode here is getting thicker. So the other observation is blue color solution fades. Okay, so I'll turn colorless. It's up to you. Okay, so but it take a long time to turn colorless. Okay, now we already know. Okay, we already know where the electron flow here. You can see some reading here. This reading, right, is E theta cell. The reading here, if you do it like this, okay, we see the calculation first at the bottom here. E theta cell, we take the reduction. So you know which one is reduction, right? It is copper. Copper is going through reduction. So you take the reductions, the E theta reduction 0.34 minus the E theta oxidation. E theta oxidation. So we have to take the original value. To take the original value to minus. So we take the original value from data booklet to minus. So minus with negative 0.76. Of course, at the end, you end up with plus. So you get 1.10. The 1.10 volt, right, is actually the reading of the voltmeter here. So it's reading of the voltmeter. So compared to last time, right, when you put SHE over here, the reading is 0.34 volt, the reading from the data booklet. But now when you compare to two different half cell, which is no SHE, no standard hydrogen electrode, then the reading here is the difference between these two. Okay, so which is 1.10. Now let's see the point here, anode. So anode is negative electrode. It's negative electrode now. In Voltaic cell or electrochemical cell, it is negative electrode. Compared to electrolytic cell that we learned before, it is actually a positive terminal. Okay, so I put a note here. Anode in electrolytic cell is positive. It's positive, but anode in electrochemical cell or voltaic cell is negative. So that is the difference, So I have to remember that. And who is going to be anode? So the one that is more negative. You compare this and this is more negative, so this become anode. And the one that is more negative will form negative terminal. So there is a relationship here and there. So E theta of half cell is more negative or less positive also can. Okay, more negative or less positive, it means the same. And that means they tend to go backwards. So what happens then is the metal loses electrons that forms positive ions. So you can see here zinc change to zinc 2 plus, they form positive ions. Oxidation occurs. So it's true also because this is when you go backward, that is the loss of electrons. Loss of electron means oxidation. And beside loss of electron, you can also think of increase in oxidation number. The oxidation number of zinc atom is 0, but when they go backwards, they form zinc 2 plus, right? So the oxidation number is positive 2. So there is an increase of oxidation number from 0 to positive 2. So remember that, that is oxidation. Okay, so how about anode in electrolytic cell? So it is positive, that is opposite from this one, but it goes through oxidation also. Yeah, that is the similarity. Go through oxidation. So you can see something same and something opposite. Oxidation is same. Okay, oxidation is same. That means no matter electrochemical cell or electrolytic cell that we learned before, anode goes through oxidation. the difference is electrolytic cell has positive as anode, but electrochemical cell has negative as anode. Okay, so anode is negative. Anode is negative in electrochemical cell, but in electrolytic cell, anode is positive. So we have something same and we have something different over here. Now, let's look at cathode. Cathode is just the other way around. Cathode is positive electrode. It's positive electrode. So again, I put it here so that you can compare and remember this. Cathode, cathode in electrolytic cell is negative. It's negative. So if you still remember, cathode will attract cation. Cation is positive, so they will attract cation. So, and the other thing is go through reduction. Go through reduction. So go through reduction is the common properties between the two cells, but the cathode, which is negative in electrolytic cell, right, is different from electrochemical cell. Electrochemical cell, it has cathode as a positive terminal. So who is going to be cathode? So you have to look at the data booklet. You take the one that is more positive. As in here, you see copper, the E theta is more positive, so it is taken as cathode. Okay, so E theta or half cell is more positive or less negative. So less negative is like, let's say you have two values that are negative. This is negative 0.36, this is negative 0.34, for example, negative. Then between the two negative value, negative 0.34 is considered less negative. That is taken as cathode. So we use less negative when we have two values that are both negative. Then we compare. Whoever that is less negative will be taken as cathode. So metal ion gain electrons. So I already explained this. Cu2 plus gain electron to become Cu, and Cu make the cathodes thicker. Okay, solid metal deposited, deposit on the electrode. For this case, reductions occur. Reduction occurs because the reduction means accept electrons, or in other words, the oxidation number from positive 2 to 0. That is also reduction. Okay, now we continue. Cell notation. Cell notation, we have a fixed format. You have to remember what kind of format to be used here. Okay, so this is the format to write cell notation. We put anode half cell on the left, and we put cathode half cell on the right. For the anode half cell, we start with electrode first. Let's start with electrode first. Start with electrode, and then zinc 2 plus. Zinc 2 plus is the electrolyte. Electrolyte. So on the other side, we start from right hand side. Right hand side, we put electrodes. Then followed by, we draw a vertical line to show phase boundary. Phase boundary means they have different physical state. This is solid, this is aqueous. So different physical state, we put phase boundary as a vertical line. So after that, after the electrodes, we put the ions. So we put ions. We put ions here, and it is Cu2 plus. Okay, Cu2 plus, aqueous. Okay, so in between of the anode and cathode, we put two vertical lines to show the salt bridge. Okay, so you can see salt bridge here. Salt bridge I explain later. What is the function of salt bridge? We will take a look after a while. Okay, so now let's move on. After you know this, it is good to see more example. Okay, let's say one more example. Okay, let's say if I try to use this one. Okay, if this is my half cell, I mean if this is my electrochemical cell, how am I going to write the cell notation? Okay, if this is my electrochemical cell. So let's take a look. We try to compare. Okay, we have to put anode on the left. Okay, I have to put anode on the left. So we already decide from our previous discussion, anode is the standard hydrogen electrode. So anode put on the left. So I have to put the electrode first, like what we discussed just now. We put electrode first. So the electrode is platinum. So we put platinum first. So the cell notation. We put platinum first. Platinum is solid. So then we put a phase boundary. Phase boundary. Why phase boundary? Because, okay, let me repeat again. We put phase boundary because this is solid and this is aqueous. This is gas. So there are different physical states: solid, aqueous, gas. So that's why we put phase boundary. So after you put phase boundary, right? So what to do is, which one should we put first? H plus first or H2 first? So we need to know about that also. The idea is, when you go towards the salt bridge, okay, from the end of the from the electrode, let's say from the electrode, when you go towards the salt bridge, the oxidation number increases. Oxidation number increases when you go towards the salt bridge. Oxidation number increases. So for example, you see zinc, then zinc 2 plus. Then you see here from the electrode, oxidation number increase. Copper, copper 2 plus. Oxidation number increase when you go towards the salt bridge. Okay, so which means, okay, let me write down this thing. When you go towards the salt bridge, oxidation number increase. This side same also. When you go from the left hand side towards the salt bridge, oxidation number increase. Okay, so because of this, right, then we can decide easily already. The oxidation number of H2 is actually 0, and this is positive 1. So 0 comes first because oxidation number increase, right? So we follow the ascending order: 0, then positive 1. Okay, so we put like this. We put H2 gas first. Okay, so followed by H plus. H plus aqueous. Okay, the thing is, what should we put over here? What should we put? We have to put another vertical line because they are in different phase, different physical state. So we have to put another vertical line here to show phase boundary. Okay, so you can see two vertical line has been used, followed by double vertical line to show salt bridge. Okay, followed by right hand side where we have to put our cathode, the cathode half cell. So cathode half cell is this one. We already decide cathode. So we start from the electrode at the end. So I will put it here. Copper solid, followed by copper 2 plus, So Cu 2 plus, aqueous, put phase boundary, a vertical line. So that is how we represent the cell notation for this case, which is a little bit more complicated. Okay, so now let's see. Okay, now I give one more example on how to write cell notation if we have something like this. If we have something like this, where I purposely use Fe2 plus, Fe3 plus. Both are aqueous. And this is, let's say, the platinum platinum. So let's say here I use, let's say this one I use the normal one. Let's say I connect it to SHE. I connect it to SHE. So we want to practice on how to write the cell notation for this case. Okay, so first of all, we have to look at the data booklet. Okay, we have to look at the data booklet to find out the E theta for Fe3 plus and Fe2 plus. Okay, so of course SHE we already know. SHE is 0 volt, but the iron we have to look for it. So if you have your data booklet with you, of course if you don't have it, just take the value straight away from here. Okay, so the Fe3 plus, this is from data booklet, Fe3 plus receive electrons become Fe2 plus. The E theta is 0.77 volt. Okay, so that is for iron 3 plus to iron 2 plus. The SHE, right, is actually the H plus electrons, then become H2. So the E theta is 0.00 volt. Okay, so now let's understand it in the same way. So first, let's say I want to decide who is more positive and who is more negative. So obviously 0.77 volt is more positive, so we should expect it to go forward. And 0.00 volt for the hydrogen, the SHE, is more negative, so we should expect it to go backwards. Okay, so I just draw an arrow here, go backwards. Okay, so if it goes forward, that means it is going through reduction. Going through reduction means cathode. So we should expect this as cathode. Let me label it cathode. Cathode. And the other side, the hydrogens to hydrogen positive ions, that should be anode, because oxidation happens here. So I just label this as anode. Okay, I don't draw out the SHE because I want to save time. So in fact you have to draw as in here, okay, like this, something like this. So we just focus on how to write the cell notation. Okay, so cell notation for the SHE, we have to start from SHE first. As I said before, we start from anode first. So the cell notation, I just put it here. Cell notation for this case. Okay, we start with SHE. You know, SHE, you can refer to this, of course. We use platinum as the electrode. So we put platinum first. Platinum solid. Okay, phase boundary. When you go towards the salt bridge, it is the oxidation number increases. So we should put H2 first. Oxidation number is 0, followed by H plus. Okay, then double line. Okay, this is aqueous. Okay, now on the other side, we have to put the other half cell, which use Fe2 plus and Fe3 plus. So the electrode used is platinum. I start from the side, platinum, solid, phase boundary. Okay, so like what I mentioned just now, as you can see here, when you go towards the salt bridge, the oxidation number has to increase. So we have to start from Fe2 plus first, followed by Fe3 plus, so that the oxidation number increase. So Fe2 plus should be here. Okay, lack of space, I put the aqueous down there. Then followed by Fe3 plus, aqueous also. Okay, and this time, right, what am I going to highlight here is, this time we cannot use phase boundary anymore. We cannot put a vertical line anymore, because they are in the same physical state. Both of them are aqueous, so you don't draw a vertical line. You write a comma. a comma. So just write a comma, as you can see here. Okay, we write a comma. So if they are in the same physical state, we write comma. Different physical state, we write phase boundary, the vertical line. So this is the third example. Now we just move on. Okay, here. The more negative the E theta, the more easily it get oxidized. So like what I said, very negative, go backwards. That is oxidized. That means it is the stronger reducing agent. You know, if they oxidize, then zinc is a reducing agent. So the idea is like that. Reducing agent is going through oxidation itself. It reduces others. It reduces copper 2 plus to copper, but zinc itself is reduced. Now here, right hand side, the more positive the E theta, as you can see Cu2 plus is more positive, the more easily it gets reduced. So it is going through reductions, and hence it is a stronger oxidizing agent. So who is the stronger oxidizing agent? You must mention the reactant. The reactant here is Cu2 plus. Cu2 plus is the oxidizing agent. Don't say Cu. Cu2 plus is the oxidizing agent. We say the reactant. Like just now, zinc go backwards. So zinc is the reactant. So zinc is the reducing agent. Don't say zinc 2 plus. Say zinc. Zinc is the reducing agent. We always say the reactant, As you can see this equation. Okay, zinc is the reducing agent. Cu2 plus is the oxidizing agent. So this is what I mentioned just now. The one that is more negative, go backwards. The one that is more positive, go forward. And then how they get this overall equation, it is in fact, you do like this. You have to swap one. Okay, you have to swap one. So let's say I just put it up here. Okay. Zinc become, you see I swapped the equation already. Zinc 2 plus 2 electron. And then copper 2 plus 2 electron. This one I don't swap because reduction happened to it. And then you can get overall. You cut the electron on both sides of the equation, and then you get overall. Everything on the left, you keep it on the left. And everything on the right, you put on the right. So like this. That is how we get overall. And the last part I discussed already. So you can see here the calculation of the E theta cell. Okay, so we have done. And now let's see the following part. I think you should realize there is a theta there. A theta. Okay, the theta here. The theta here doesn't mean angle, Not like mathematics. Theta is angle. So over here, what is theta? Theta means standard conditions is used. Standard conditions, many conditions. Standard conditions are used. So the first condition is temperature of 298 Kelvin or 25 degrees Celsius. That means the electrolytes have to be 25 degrees Celsius. The pressure is 1 atm. So you do it at do it on the Earth's surface, for example. So the pressure is 1 atm. The concentration is 1 mole per dm cube. So that means, is it 1 m? 1 m means 1 mole per dm cube. Okay, you must follow the standard conditions. Okay, so now when you look at this page, right? So let's see 2.6 salt bridge. Okay, salt bridge. So just now we never discussed anything about salt bridge. So let's understand it now. What is the function of salt bridge here? So I will use back the same electrochemical cell like just now. So where here they put zinc. Okay, they put zinc. Here they put the zinc 2 plus. Then the salt bridge is like this. Okay, this is the salt bridge. And then the other side they use the copper, Cu2 2 plus, and then the electrode that they use is Cu. Okay, Cu, then they put the Voltaic cell like this, the circuit, connect to the voltmeter. Okay, so this is the same electrochemical cell just now. If you look at page 2 just now, right, they realize that they put something like this. They put chloride. They put chloride to the left, Cl minus to the left, and at the same time they put K plus also. But K plus, if you see the notes, they don't put any arrow for the K plus. Then they put here with some labeling here. So if you can see here they label with Cl minus, and here they label with K plus. K plus, okay, so we have to understand what happened to the salt bridge there. Okay, now let's take a look here. The first point, the function of salt bridge used to complete the electric circuit, allowing the movement of ions between two half cells so that ionic balance is maintained, electrically neutral. So it means that, so let's imagine, we start from the reaction again. The reactions on the left is zinc become zinc 2 plus 2 electrons. That is equation on the left. We already discussed that. And the electron goes away through the external circuit. So as you can see, they go from left to right. So the electron move in that way. So what can I say here is, left hand side, the half cell on the left, the negatively charged electron keep going away. The positively charged zinc 2 plus keep producing. So it will make the half cell on the left getting more and more positive. Okay, more and more positive. So I think it should make sense to you. So first point, electron going, electron go away. Second thing, zinc 2 plus produce. Okay, so zinc 2 plus keep producing and electrons keep going away, and the consequence is the half cell is getting more positive. So to avoid this, or maybe you feel like, oh, getting more positive, what's wrong? Nothing wrong, is it? Or is there any problem? Actually, there is a problem, So, but what kind of problem is that? We look at the other half cell first. Okay, the other half cell. The other half cell. Let's see the equation first. Cu2 plus 2 electron becomes Cu. So this is the equation. And after that, let's see what happened. The first thing is electrons keep coming here, keep going to the copper half cell. So keeps coming. And number two, number two, the second problem is Cu2 plus is decreasing. Okay, so you should expect the positive ion keep decrease in amount, and then the electron keep coming. So the overall effect is the half cell is getting more and more negative. So the half cell is getting more negative. More negative. Huh? So, okay, the problem that I said just now, what happens if the half cell is getting more positive on the left and more negative on the right? So eventually, the the reaction will stop. Yeah, the reaction will stop if you don't do something. The electron will, I mean, the the reaction will stop. Logically, it is true because you see, if here is getting more and more negative, the electron don't want to come here because negative and negative will repel. Okay, will repel. So electron don't want to come here, then stop already. So that's why we need to overcome the problem. We don't want to make here getting more and more negative. Okay, or else electron come here and repel away. We don't want to make here getting more and more positive. If this is too positive, electron don't want to go away because electron tend to attract by the positive half cell, So we don't want it to be more and more positive, or else electron don't want to go away. It is attracted backwards somehow. Okay, so we don't want that. And because of that, we use salt bridge. So we use salt bridge. So this is the salt bridge. What is inside salt bridge is potassium chloride, or sometimes potassium nitrate is a good choice also. For this case, potassium chloride is fine. How we know which one is fine? You have to understand insoluble salt. If the chloride come here and let's say zinc chloride, they form zinc chloride, right? Zinc chloride is a precipitate, if let's say, but zinc chloride is not. If they form precipitate, then zinc, then chloride is not suitable. Then you have to use nitrate instead. Okay? We don't want it to form precipitate. So chloride come here, but zinc chloride is not a precipitate. Zinc chloride is soluble, so no problem. No problem. If let's say this is silver, silver positive, silver positive and chloride will form precipitate and then not suitable to use chloride. Have to use nitrate instead. Okay, so our salt bridge normally potassium chloride or potassium nitrate. So if you don't want to take trouble, right, always use potassium nitrate, Potassium nitrate always soluble. So always soluble, never form insoluble salt, so it is safer. Okay, for this case, potassium chloride is fine. Okay, so now let's see. You put potassium chloride in the salt bridge, so it overcomes the problem. What problem? The electrically neutral. They want to maintain the electrically neutral. They want to maintain the two half cell to be neutral. We don't want it to be more positive and more negative. So in order to overcome that, the chloride will automatically move to the left. That's why you see the label chloride there. Why chloride will come here? Because here it's getting more and more positive. So the chloride will just stick to this end, and then it is not getting more and more positive. It remains neutral. Okay, this side is getting more and more negative. So the salt bridge try to overcome the problem by sending potassium to the right. They don't draw arrow, so I have to draw for you. So what happened is potassium is going to the right, so that the problem that is going to happen here, getting more and more negative, is overcome by potassium. Potassium keep coming here to make the half cell here remain neutral. So if both sides are neutral, then electrons can flow this side. So that is the function of the salt bridge, to maintain the neutrality of the half cell. The other thing is to complete the circuit. You know, a circuit must have one complete round one. So this is one round, one complete round. External circuit, then salt bridge, then electrode, then external circuit, electrode, then salt bridge. That is one round. Okay, so complete the circuit. So now let's see the next point. A strip of filter paper soaked in potassium nitrate. This is the simple way to prepare the salt bridge. Just use filter paper, put in potassium nitrate, and then it becomes salt bridge already. So the filter paper will remain wet, so that the ion can just move easily. Okay, so salt used should not react with ions forming a precipitate. Example: potassium chloride in a cell containing silver ions. Silver ions would form insoluble precipitate because silver chloride is precipitate. So then it is not suitable. So we have to use potassium nitrate in that case. Okay, now we move on. 2.7. Standard hydrogen electrode. Standard hydrogen electrode. Okay, SHE. So we already discussed this, and now it's just revision only. It is a reference cell. So we use it as reference cell because the E theta is 0.00 volt. It never contribute any value to the voltmeter. Okay, so the value is totally come from the other half cell. So that's why when you use SHE here, so the value here can straight away become our E theta. Okay, can become the E theta that we use in the data booklet. So that's why we call it a reference cell. So used to measure E theta of any other half cell. So you want to find the E theta of zinc, you put zinc connect to SHE. You want to find the E theta for chlorine, you put chlorine connect to SHE. So you want to find the E theta for Fe3 plus to Fe2 plus, then you connect to SHE. So that is the function of SHE as a reference cell. We draw like this. Okay, we draw like this. We draw a tube with, you see the hydrogen gas at 1 atm under standard conditions. Okay, so the gas has to be 1 atm, and then the concentration has to be 1.00 mole per dm cube. Okay, now let's see. It fulfills the standard condition. So second point, consists of hydrogen gas at 298 Kelvin. This is the room condition. 1 atm, bubbling around a platinum electrode in contact with an aqueous solution of H plus ion at 1 mole per dm cube concentration. So example, if you are using HCl, then your concentration has to be 1 mole per dm cube. If you are using sulfuric acid, H2SO4, then your concentration has to be half of it, have to be 0.5 mole per dm cube. Of course, the reason is because sulfuric acid supplies 2 times of hydrogens compared to HCl, 2 times. So concentration of 0.5, then you times 2, then you get 1.00 mole per dm cube. That's the standard concentration. Okay, so why platinum? Now they explain it here. Platinum as the electrode. So why? Platinum electrode is inert, allows conductions, and is coated with finely divided platinum, serving as a catalyst. Finely divided platinum. So that means like many sphere. So there are space in between the sphere. So that's why they say being porous. Being porous means have space in between the atom. That is porous. So retain large amount of hydrogen gas. You know the hydrogen gas that go in, right? So they can just stay in the space of the platinum's atoms. Stay in the space in between. Okay, something like this, stay around here, stay inside. Yeah? The gas stay inside the empty space between the sphere. And after that, so what happened is, the reactions is either go forward or go backwards, depends on the other half cell. So if the reaction is, the reaction is like this, H plus 2 electrons become H2. So to know whether it go forward or go backwards, it depends on the other half cell. Like what I said, whoever that is more positive go forward. So if let's say it go forward, if it goes forward, then we will follow this one. I will follow this one. Okay, this one. Maybe I draw a box here. So H plus go into the small hole in between of the platinum atoms to find the to get electrons, and then they form H2. They form H2. Okay, to form H2. This is where when it go forward. Okay, now let's see the other one. Okay, this one I use blue color. Okay, so what happened here? Sometimes the reaction have to go backwards. Depends on which half cell is pairing with the hydrogen. Okay, so sometimes they have to go backwards. So going backwards means hydrogens become H plus. So hydrogens is already inside the platinum, so they will donate the electrons, and they come out as H plus. Okay, so you can see something like that. Okay, so by the way, I haven't balanced the equation. The circle here remind me H2 is two atoms, and then the form H plus is two separated balls. Okay, so it break down. The covalent bond in between break down to two smaller balls. Okay, so we settle already. Standard hydrogen electrode. Now this one we also discussed already. The time I said you want to measure E theta, you have to connect it to SHE. So now we just go through as a revision. So if you use these three diagram, right, is trying to tell us on how to draw it out. Okay, we need to know how to draw it out. So if you use zinc, connect to standard hydrogen electrode, and the reading shown is 0.76. Okay, 0.76. So that means the 0.76 is because of zinc, not because of SHE. SHE contribute no value, so it's because of zinc. And because of that, the E theta for zinc 2 plus to zinc is 0.76 volt. Positive or negative, we decide in this way. If the voltmeter is using negative terminal to connect here, then it's negative. It's negative. If the voltmeter is using positive terminal, to connect to this half cell, then it's positive. So I just draw an arrow. So this negative affect this E theta, the sign of the E theta. Okay, now we move on. Compared to the second one, the second one we use non-metal now. Just now is metal. Metal is kind of easy. The metal itself become electrode. The ions become the electrolyte. But when it's non-metal, right? Non-metal, if it's non-metal, like chlorine gas, then we have to use platinum as electrode. The chlorine gas has to channel in by using this this tube, okay, and then the electrode, the ions stay in the electrolyte. So the diagram is like this, and this diagram same like the standard hydrogen electrodes. Okay, but non-metal can be liquid, can be aqueous also. So if they are liquid or aqueous, then you draw like this. You draw like this, huh? No need to have this tube ready. So just put the liquid inside the container straight away. Okay, so okay, let's discuss this first. Like what I said, the reading here is because of chlorine, not because of SHE. SHE has no value, it's 0.00 volt. So this value is totally from chlorine. Huh? So the E theta, so let me write now, the E theta for reduction we write chlorine to chloride, okay, is 1.36 volt. 1.36 volt. Positive or negative, you just look at the voltmeter. The positive terminal connect to chlorine, then it is positive. Okay. Then the next one, this one. So like what I say, if both are aqueous or both are liquid, then you can just put both inside the container straight away, the beaker. Okay, inside the beaker straight away. And then this one's SHE again. So the reading here is 0.77. Okay, so it means your E theta for Fe3 plus to Fe2 plus is equal to 0.77 volt. And it's positive or negative, you see the voltmeter. It's positive, is connected to that side. This is positive. Okay, so we settled this page already. Now let's move on to the next page.